This call is now being recorded.
Okay, so this is our circuit diagram for the common source amplifier followed by a common drain amplifier, or we can say source follower. Okay, now we have drawn the equivalent circuit. Okay, so ഇത്രയും വരെ complete ആണല്ലോ എല്ലാവരുടെയും. So this is the equivalent circuit, that is this is the common source part and this is the common drain part. Now we have to do the analysis. So first we can consider, that is analysis means we have to find the voltage gain for this configuration. Okay, so first of all we have to write output voltage. V out is equal to, you can see here output voltage is taken across this resistor RL, right? This is our output voltage RL. Now the voltage across the resistor RL will be equal to what? That is, here we have at the output terminal the current is GM2 into VGS2. Okay, ഇത് നിങ്ങൾ ഇങ്ങനെ വരച്ചുകൊണ്ട് കൺഫ്യൂഷൻ ആവേണ്ട, വേണമെങ്കിൽ നമുക്കൊരു കറന്റ് സോഴ്സ് ഇതേപോലെ റെപ്രസെന്റ് ചെയ്യാം. That is, here this is the ground terminal and from ground upward direction to the source. This is our source terminal here, and here you have this RS2 and this RL, right? Both are connected to ground, and we are taking this voltage. This is our output voltage. So while considering the output voltage, we have the current GM2 into VGS2, and the resistance is the parallel combination of RS2 and RL, right? So we can write output voltage is equal to what? GM into VGS2 RS2 parallel RL, right? So I am taking this as equation 1. So output voltage is equal to this GM2 into VGS. Okay, GM2 current in direction same ആണ്, so that we can take positive. Okay, GM2 into VGS2 into RS2 parallel RL. That is the output voltage. Okay, so this is our output voltage. Now I can write this output voltage plus this VGS2, that will be equal to the voltage across the resistor RD1. That is, here you can see, നിങ്ങൾ ഈ ഒരു സർക്യൂട്ടിൽ കാണുന്ന വോൾട്ടേജസ് ഒന്ന് ചെക്ക് ചെയ്യാം കേട്ടോ. So here you will be having at the output part you have V0, okay, output voltage, and here you have one VGS2. Okay, so this is negative positive V0, here also it is negative positive VGS2. So we can say this V0 plus VGS2, these voltages, sum of these voltages VGS2 plus V0, that should be equal to the voltage dropped across this resistor RD1, right? Or we can say simply we are applying KVL here. You can say this V0, this V0 plus VGS2, that will be equal to the voltage drop across the resistor RD1, right? So this V0 plus VGS2, that should be equal to the voltage drop across RD1. So what is the voltage drop across RD1? Voltage drop across RD1 will be equal to this current into resistance, or we can say it will be minus GM1 into VGS1 into RD1, right? So the voltage drop across the resistor RD1, that is equal to GM1 into VGS1 into RD1, right? So this will be equal to sum of these voltages, that is VGS2 plus V naught. So we can write V naught plus VGS2 will be equal to minus GM into VGS1 into RT1. Okay. Now from this equation, I can write VGS2 is equal to minus GM into VGS1 into RD1 minus V naught. Okay. Now what is this VGS1? VGS1 means this one. Okay. This is VGS1. So this voltage will be equal to, that depends upon the input signal voltage, right? VSI. So we can say if you are applying an input signal VSI, this voltage will divide between these two resistors, that is between RSI and R1 parallel to R2. Let this R1 parallel to R2 equal to RI. Okay. So then your combination replacing with RI. So we can say this VSI will divide between RSI and RI. Okay. So by applying voltage division rule, this VGS1 is actually the voltage drop across this parallel combination of R1 and R2. Or simply we can say voltage drop across RI. So by applying voltage division rule, VGS1 will be equal to what? This VSI into RI divided by RSI plus RI. Okay. So we can say here, but VGS1 is equal to VSI into, that is input signal, into RI, that is parallel combination of this. RI means parallel combination of R1 and R2. Okay. Divided by RI plus, that is total resistance, RI plus RSI. Okay. And now substitute for VGS1 in this equation. You will obtain this VGS2 is equal to minus GM into VGS1 means this VSI into RI divided by RI plus RSI, right? Into RD1 minus V naught. So this is our VGS2. I'm taking this as equation number 2. Now you can substitute this VGS2 in equation number 1. Actually, our aim is to get the voltage gain V out by V in. Okay. So in order to represent the voltage, all the VGS voltages in terms of this V in and V out, we are doing all these things. So now substitute equation number 2 in equation number 1. Okay. So what will happen? V out is equal to what? GM into, instead of VGS2, we have to substitute this value. That is GM into minus GM VSI into RI divided by RI plus RSI. നിങ്ങളുടെ നോട്ടിൽ ചെയ്യണേ, അല്ലാണ്ട് ഇത് വെറുതെ നോക്കിയിട്ടൊരു കാര്യമില്ല. Okay. Into RD1 minus V naught. Okay. This is GM into VGS2 into RS2 parallel RI. So this is our expression for output voltage. Now you can simplify this. That is output voltage is equal to, I am multiplying with this GM2. Sorry, here output voltage is actually, this is GM2. That is, here it is GM2 into VGS2, right? So this is GM2 into VGS2. This is GM1 into VGS1. On the 1 into mark here. Okay. So this is GM1, this is GM2. Okay. So now I can write minus GM1 into GM2 into this Ri divided by Ri plus Rsi into Vi into Rd1 minus, so I'm multiplying with this GM2. Okay, so minus GM2 into V naught. Okay, into this RS2 parallel RL. Right. Now I can take the term with the V naught or V out to the left side, so that I will get here it is V out, and here you have a term with the V out here, that is minus GM2 into V out into this RS2 parallel RL. So I'm taking to left side, that is this minus will become plus GM2 into V naught into RS2 parallel RL, right, is equal to minus GM1 into GM2 into, I can say, Ri divided by Ri plus Rsi into Vi into Rd1 into this Rs2 parallel RL, right? Okay. Now here you can take V out common, this 1 plus GM2 into V naught into Rs2 parallel RL is equal to minus GM1 into GM2 into Ri divided by Ri plus Rsi into Vi into Rd1 into Rs2 parallel RL. Right. Now we can write the voltage gain, that is equal to what? V out by Vin. Okay. So V out by Vin means here you have V out and here you have Vin. So take this Vi to left side and take this term to right side. Okay. So I can write V out by Vin. So V out by Vin means here you will be having this terms, that is minus GM1 into GM2 into Ri divided by Ri plus Rsi, okay, into this Rd1 into Rs2 parallel RL. Okay, that will be on the right side, and this term, that is divided by this 1 plus GM2 into, sorry, we out outside of the okay, 1 plus GM2 into Rs2 parallel RL. Right. So this is the total voltage gain of this cascade configuration of common source amplifier followed by common drain amplifier. Okay. Is it clear? Clear or no? Okay. ഞാൻ ചെയ്യുന്നതിന്റെ കൂടെ തന്നെ നിങ്ങൾ ചെയ്തു കഴിഞ്ഞാലേ ആ സ്റ്റെപ്സ് ഒന്നുമില്ല, കുറച്ച് വലുതാണെന്നേ ഉള്ളൂ, സിമ്പിൾ റീഅറേഞ്ച്മെന്റ്സ് ആണ്. ഓക്കെ, അപ്പൊ ചെയ്യുന്നതിലൂടെ ചെയ്താലും നിങ്ങൾക്ക് അത് മനസ്സിലാവുള്ളൂ, അല്ലെങ്കിൽ വലിയ എന്തോ ആയിട്ട് തോന്നും. ഓക്കെ, now so this is about cascade amplifier. Now what is the main drawback from this is, here you can see the voltage gain increases in cascade. You use cascade configuration, you can increase the voltage gain. Okay, but we can say, as we already told, here using cascade amplifier you can increase the voltage gain, that is gain increases from this value to this value. Okay, but our bandwidth reduces, right? our bandwidth reduces from this to this value. Okay, so this is the one trade-off in cascade amplifier, that is gain increases as the number of stages increases, our gain increases, but bandwidth get reduces. Okay, so that we are going for next configuration called cascade amplifiers. Okay, cascade amplifier. This is also an example of multi-stage amplifier, but our connection is different. In cascade amplifier, we are taking output from one stage and we are giving it as the input to the next stage. Okay. In cascade amplifier, we are not connecting like that, but we are using more than one stage of amplification. Okay. So in cascade amplifier, what is the advantage is that we can improve the gain. Also, we can obtain large bandwidth. Okay. So we can say by using cascade amplifier, you can obtain high gain. This you can improve the gain and large bandwidth. Okay, so this is the main advantage of cascade configuration. Let us see one example for this cascade configuration using MOSFET. Here also, what we are doing is we are connecting together a common source configuration and common drain configuration. Okay, so we are using two different amplifier configuration, common source and common drain. Okay, so first of all, I am taking a common source configuration, that is using an NMOS. Here I am considering a common source configuration. Using voltage divider circuit and a source resistor is there. Here there will be a bypass capacitor. It will be transistor Q1. Okay. Now, and to the gate of this common source configuration, I am applying input signal. This is input signal. Okay. And now to this drain terminal. Normally we are connecting this drain terminal to the load, right? To this drain terminal, we are connecting RD or some current source. Okay, we are connecting any load to this terminal. Instead of that, here we are using a common drain amplifier at this terminal, right? So here, before connecting to load, we are using another configuration, that is another stage of amplifier, that is common drain amplifier. Sorry, not common drain, it is common gate. Sorry. Common source and common gate. Okay. So here we are using a common, we are going to use a common gate configuration. Okay. So this common gate configuration is also applied with a voltage divider biasing. And this source is connected to drain. That is, this is the source of common gate configuration that is connected to drain of our common gate configuration, common source configuration. Okay. And here, since it is common gate configuration, common gate means we are connecting this gate terminal to ground. Okay. Connecting this gate terminal to ground. In common source configuration, we are connecting source to ground, right? In common gate configuration, we are connecting gate to ground. And now to this terminal, you can connect the load resistor RD. Okay. Here you can connect the supply voltage. So this is the, I can say this is a cascode configuration. In this cascode configuration, this part is common source amplifier, and this part represents common gate configuration. Okay, common gate means gate is connected to ground. So this is the cascode amplifier. Here we are connected this Q1 in common source configuration and connected Q2 in common gate configuration. And the advantages of this circuit is high gain and large bandwidth. Okay. Now, for the analysis purpose, if you are doing small signal analysis of this circuit, this will become very complicated. Number of resistors, capacitors, connection, the circuit will be complicated. So for the small signal analysis purpose, we are not considering the biasing resistors and capacitors called. Okay. So small signal analysis is simpler to say. We are not considering this circuit. We are simply considering this common gate and common source configuration only. Okay. R1, R2 biasing resistors, load resistor consider source resistors, and the biasing consider we are going for the small signal model. Okay. So for the cascode amplifier analysis, for the small signal analysis, so small signal analysis of this cascode amplifier. Okay. For this, I am taking these two MOSFET only. That is, here you have that common gate, that MOSFET connected in common gate configuration. That is, we are connecting this gate to ground. Okay. And here, this is connected to the common source. Source is connected to ground. Okay. So we can say this is our Q1 and this is our Q2. Now this Q1 is in common source configuration. That is, let it be this source 1. Source of this Q1, S1, and this is D1, drain. Okay. And this is gate 1. And for between this gate and source, or we can say to the input of this common source configuration, we are applying our input signal. That is, here we are applying input signal Vi. Okay. And for Q2, actually this is source. This terminal is source and this terminal is drain. This is gate. Okay. So D2, G2, S2 are the terminals of Q2 and D1, S1, G1 are terminals of Q1. Now, this D2, for the simplicity, here I am assuming, initially I am assuming this is connected to load. So, load this drain is connected to some load. So, actually drain. So, drain RD load connected. Okay. So, for this analysis purpose, we are simply taking load simply we are taking this terminal will be connected to the load. Okay. So, for the small signal analysis, we are considering this circuit. So, this lower part represents common source amplifier and upper part represents common gate amplifier. Okay. Now, here we are going to obtain an equivalent circuit like this. That is, your cascode configuration, how you will obtain the equivalent circuit. Normally, at the output side, we are considering only at the output side because input side and then biasing but gain determines again, it is enough to consider the output side. So, for this circuit, we are drawing an output equivalent circuit. An output equivalent circuit for this cascode configuration. Okay, we are considering output equivalent circuit for this cascode configuration. There is a voltage controlled current source. We can name it as GM into Vi and a parallel resistor R0. Okay. So now we are going to find the values of GM and R0 for this cascode configuration. Okay. So this is our drain 2, which is connected to load. which is connected to load. So our aim is to determine what this GM and we have to determine this GM and R0 value in order to get the output equivalent circuit for this cascode configuration. Okay. So first of all, we can find this GM. Okay, GM value. So in order to calculate this GM value, in order to determine GM, what we are doing is we are connecting this drain terminal to ground. Okay, so that we can say when we are connecting this drain terminal to ground, that is if you are considering or if you are connecting this drain terminal to ground. Okay, or we can say in equivalent circuit, if you are connecting this drain terminal to ground, then what will happen? We can write, that is here point when D2 is short circuited to ground, we can say the current through output. Okay, the current through output, that is I0, will be equal to GM into VI. That is, if you are connected to ground and we are assuming there is a current I0 to this direction. Okay, if you have a current in this direction, if it is short circuited, then there will not be any effect for this R0. This I0 will be equal to this current, that is GM into VI. Okay, so in order to find the value of GM, actually നമുക്ക് വേണ്ടത് ഈ ഒരു കാസ്കോഡ് കോൺഫിഗറേഷൻ ഒരു ഔട്ട്പുട്ട് ഇക്വിവാലന്റ് സർക്യൂട്ട് വേണം. So the output equivalent circuit should be like this: a voltage controlled current source in parallel with a resistor R0. Okay, so in order to draw this, we have to consider the drain terminal is connected to ground. The drain terminal ground connected aanengil we can assume a output current I0 that will be equal to GM into VI. Okay, output current I0 will be equal to GM into VI. Right? Now, so we can find, using this equation, you can find GM. That is, GM will be equal to what? Is I0 divided by VI. Now, consider that case, that is, here, this is our gate 2, this is our gate 1, and here you will be having this source 2, and this is drain 2, this is drain 1, this is source 1. That is your common source configuration with the common gate configuration. Okay, now this common source terminal is grounded. Here this gate terminal is grounded, and between this point we are applying the input signal. Okay, and now in order to calculate GM, first aim is to calculate GM. So for that we are connecting our D2 to ground, drain terminal, and we are assuming a current I0 here. I0 will be equal to what? GM into V. Okay, now in order to calculate GM, consider small signal equivalent model of this circuit. That is, we have to replace these transistors with the small signal equivalent model. Okay, so first I am considering the lower transistor Q1. So I can draw the small signal equivalent model for this combination. For Q1, I can draw the small signal equivalent circuit like this. That is, here this is the gate 1 terminal, and for the small signal equivalent circuit of MOSFET, this will be what? This will be VGS1, right? And this is source 1, this is gate 1, this is VGS1, and here I can draw the drain 1. So between drain and source, we will be having GM1 into VGS1, right? And you will be having a parallel resistance R01. Equivalent circuit marker and this R01. Okay, so this is the equivalent, small signal equivalent. This source is connected to ground and we are applying input signal here. Okay, so this is the equivalent circuit for the transistor Q1. Now, this position transistor for the corresponding to transistor Q2. Here, drain 1 is connected to source 2. Okay, so this is my drain 1 terminal. So this point, to this point, I can connect the source 2. Okay, so actually this is the common point for drain 1 and source 2. Okay, that's the other point. Now to the source, what we have here it is source, that is this is source terminal. So here I can take this as the gate terminal G2. Okay, so between this is source, this is gate. So here I can take this is VGS2, right? And this gate 2 is connected to ground. Okay, this drain 1 and source 2 are same. So this point, this line, that is drain 1, I can take it as source 2. So between this source 2 and gate 2, we have VGS2. Okay, and between this source and drain, this is source 2. So between this D2 and S2, that is drain 2 and source 2, we will be having this GM2 into VGS2. That is corresponding to this Q2. That is Q2 into equivalent small signal model. This is VGS2, this is GM2 into VGS2, and you will be having R02 here. Okay, this is R02. And this is my drain 2, which is connected to ground. And we are assuming the current is I0. Okay, so this is the small signal equivalent circuit for this cascade configuration. So we will do initially this point mark our complete aim is this cascade configuration corresponding to output equivalent circuit form. So in this output equivalent circuit, we have to calculate the GM and R0. We have input signal GM and R0. So this GM calculate we consider this drain terminal ground lake connected. Okay, so drain terminal ground lake connected, we have considered the small signal equivalent. Okay, now we can see how will you obtain the capital letter GM. That is GM is equal to actually I0 divided by VI. Okay, so this I0 and VI and so from this equation we can find capital GM. Now, note one point here, that is G2 is connected to ground, right? This G2 is connected to ground. So we can say across this R01, the voltage will be minus VGS2. Actually, VGS2 ground. So voltage across R01 will be minus VGS2. Now applying KCL. First you have to apply KCL. Applying KCL at drain 1, or we can say at source 2. That is your point here. We are applying KCL. Okay. So before applying KCL, we can say we can see which are all the current leaving and entering to the junction. Okay. So here we will be having this GM1 into VGS1. GM1 into VGS1 leaving the junction. Okay. And this GM2 into VGS2, that will be entering to the node. Okay. So to this node, we are applying KCL. So first consider the current entering and leaving from this point or to this point. Okay. So we can say here GM1 into VGS1 leaving the junction, GM2 into VGS2 entering the junction. And you have two resistors also connected to this terminal. That is, one is R01 and second one is R02. Okay. So both are between this point and ground. So at this point, voltage is VGS2. Okay. At this point, the voltage is VGS2. And we have to take the direction of current like this. That is, here I can say Actually, നമ്മൾ റെസിസ്റ്റർ എടുക്കുമ്പോൾ നിങ്ങൾ എന്താ ചെയ്യുന്നത്? നോർമലി കറണ്ട് ലീവിംഗ് ഫ്രം ദ ജംഗ്ഷൻ ആയിട്ട് കാണിക്കുന്നത്. Okay, but here the voltage across R01, the voltage is minus VGS2. So I am taking the current direction like this. That is, current flowing through R01 is VGS2 divided by R01. This is the current flowing to the junction. Now, coming to R02. At the R02 also, we have the current. That is, current I am taking to this direction because it is minus VGS2. So VGS2 divided by R02. Okay. So at this node, we have current entering to this node, RGM2 into VGS2, VGS2 divided by R02, and here VGS2 divided by R01. These are the current entering to the node. The current leaving from the node is GM1 into VGS1. Okay. So we can write the KCL like this. That is GM2 into VGS2 plus VGS2 divided by R02 plus VGS2 divided by R01. These are the current entering to the node. This should be equal to GM1 into VGS1, which is the current leaving from the junction. Okay. Now, take VGS2 outside from left side. VGS2 into GM2 plus 1 by R02 plus 1 by R01. This will be equal to GM1 into VGS1. Now, we can take one approximation. That is our GM2. GM2 will be far, far greater than 1 by R01 or 1 by R02. This R01 and R02 are very high values. So 1 by R01 and 1 by R02 will be very less compared to GM2. So in this bracket, while we are considering GM2, 1 by R01 and 1 by R02, this GM2 will dominate. We can neglect the effect of 1 by R01 and 1 by R02. Okay, so that I can write VGS2 into GM2 will be approximately equal to GM1 into VGS1. Okay, so we can write GM2 into VGS2, which is equal to GM1 into VGS1. Okay, so this is my first equation. Okay. So time ആയി. നമുക്കൊരു കാര്യം ചെയ്യാം, ഇതിന്റെ ഡെറിവേഷൻ ബാക്കി നെക്സ്റ്റ് ക്ലാസ്സിൽ ചെയ്യാം. കുറച്ച് ചെയ്യാനുണ്ട്. ഞാൻ നേരത്തെ പറഞ്ഞ പോലെ we have to calculate GM and we have to calculate this R0. അത് രണ്ടും വെച്ചിട്ട് നമുക്ക് വോൾട്ടേജ് ഗെയിനും കൂടെ കാൽക്കുലേറ്റ് ചെയ്യാനുണ്ട്. ഓക്കെ, നമുക്കത് നെക്സ്റ്റ് ക്ലാസ്സിൽ കൺക്ലൂഡ് ചെയ്യാം. I'm stopping here.